For my data structure, I chose WAVL trees, and they're trees that are a more relaxed version of AVL trees, as shown by their name, which is weak AVL. The rank difference between any two adjacent nodes can only be 1 or 2, and they cannot have any other value. WAVL trees contain leaves, which are just nodes that contain no children, and they will always have a value of 0. Any children nodes at that point would have a value of -1. When a WAVL tree is being rebalanced, two actions can occur to its rank. The rank can either be promoted or demoted. The rank directly relates to the height of the node, but it does not equal the node in all cases. When the rank is promoted, the value of its rank increases by 1. For example, a rank of 1 becomes a rank of 2. When the rank is demoted, the rank is decreased by 1. In this case, if the rank is 2, it will then become 1. When promotion and demotion violates the rank laws of WAVL trees, rebalancing occurs through rotation. Rotation automatically redistributes values in a direction that balances the tree. WAVL trees are self-balancing trees and therefore automatically rearrange the values of nodes to balance the tree. The values of nodes at this point are evenly distributed amongst the trees. The ability to rebalance is a major benefit to using WAVL trees over the related AVL trees, which are rank balanced. There are no direct variations of WAVL trees, but many do find the AVL tree to be its closest relative. On top of AVL trees, red-black trees, another binary search tree, are also deemed very close in structure to that of the WAVL tree. AVL trees structure their nodes similarly to that of WAVL trees, except in this case, the difference between heights of left and right subtrees cannot be more than 1 for all nodes. AVL trees have been around since 1962 for use in Big O notation, and therefore have been used more than WAVL trees. Red-black trees, on the other hand, have multiple differences. All nodes of a red-black tree are either red or black, have a black root, no two adjacent nodes are red, and finally, for every path from a node to any of its child null nodes have the same number of black nodes. WAVL trees are a combination of both AVL trees and red-black trees, which produces the most efficient binary search tree. In terms of time complexity, the height of a WAVL tree can be shown as O log n. Rotating a WAVL tree is shown as O of 1, as the rotation shifts the rank values simplistically. As shown in the table on this slide, the best and worst cases in terms of time complexity for all operations are the form O log n. This time complexity beats many of the other closely related binary search trees, as it is significantly faster. Currently, there are no languages that have WAVL trees implemented by default, and therefore must be implemented yourself. The most effective languages to program WAVL trees into would be Java, C++, and Python. Implementing WAVL trees can be done by declaring node variables. Parent nodes and child nodes must be implemented as rotation is involved through rebalancing. To rebalance, we must find the side of the WAVL tree that is unbalanced, then distribute the value of the parent node to the child nodes. In this case, any external node will have a value of 0, whereas the internal nodes will not have a value of 2. Promotions and demotions will be implemented by adding 1 or subtracting 1 from the parent node and distributing the value to child nodes based on the unbalanced side. Rotations and double rotations could be implemented by distributing values of the nodes on the side of greater nodes to the opposite side, thus rebalancing the WAVL tree. Of course, there are many intricacies involved with creating a WAVL tree algorithm, including the deletion of previous parent and child nodes through rebalancing, as well as the creation of new external and internal nodes based on the situation. If WAVL trees were a standard library, many programs could be sorted more efficiently. The sources I used to write my written compendium were a quantitative comparison of WAVL trees and splay trees, emory.edu, YourBasic, cpp.edu, Geeks for Geeks, odu.edu, and GitHub. The sources that I have linked within the written compendium provided essential information that guided me through all there is to know about WAVL trees.